Storing information in long-term memory. The way you learn information in the first place seems to affect its recall later. One important requirement is that you integrate new material with information already stored in long-term memory as you can construct an understanding. So here, elaboration, organization, and context play a role. Let's take a look at elaboration. Okay? Elaboration is what? The addition of meaning to new information through its connection with already existing knowledge. Right? So in other words, we apply our schemas and draw on already existing knowledge to build an understanding of new information and perhaps to change our existing knowledge in the process. Accommodation, equilibration, right? We often elaborate automatically. Well, even we are unaware of doing this. Material that is elaborated when first learned will be easier to recall later. Right? Now, on the other hand, elaboration is a form of rehearsal. It keeps the information activated in working memory long enough to have a chance for permanent storage in long-term memory. Okay? Elaboration builds extra links to existing knowledge. The more one bit of information or knowledge is associated with other bits, the more routes or more routes there are to follow to get to the original bit. Okay? So psychologists have found that the more precise and sensible the elaborations, the easier recall will be. Well, that is what that is in consonant with what deeper level of processing, right? So let's take a look at one organization. In organization, material that is well organized is easier to learn and to remember than bits and pieces of information, especially if the information is complex or extensive. Now, placing a concept in a structure will help you learn and remember either general definitions or specific examples. The structure serves as a guide back to the information when you need it. Okay? The structure is important, right? The context, either physical and emotional. Okay, so aspects of physical and emotional context, like places, rooms, how we are feeling on a particular day, who is with us. These are all learned along with other information. And later, if you try to remember the information, it will be easier if the current context is similar to the original one. Right? Now, this has actually been demonstrated in the lab. Okay? Students who learned material in one type of room performed better on a test taken in a similar room than they did on tests taken in a very different looking room. All right? So look at the positive transfer here, and we'll come to this, okay, later on, okay, in other lectures. So studying for a test under test-like conditions may result in what? Improved performance. Improved performance. Let's take a look at what here. Retrieval of information from long-term memory. The size of the memory network is huge, but only one small area is activated at any one time. Okay? Only the information we are currently thinking about is in the working memory, okay? Which can be what? Which can be easily overflown with information because its capacity for information is small, 7 plus or minus 2 distinct items. So information is retrieved in this network through what? Through the spread of activation. Okay, the spread of activation. Okay, this is what? This is important, right? When a particular proposition or image is active, that is to say, when we are thinking about it, other closely associated knowledge can be activated as well. And activation can spread through the network. Now, let me give you an example of the spread of activation. All right. Let's say I live in North Bay, but I have to drive to Toronto on Friday. So related ideas such as I need to go to the ATM to get some money for the trip, and perhaps the car needs an oil change. These two ideas may come to mind. You see, so retrieval from long-term memory is partly through the spreading of activation from one bit of knowledge to related ideas in the network. So that is spread of activation. However, if spreading activation does not find the information we seek, then we might still come up with the answer through another way called reconstruction. That is a problem-solving process that makes use of logic, cues, and other knowledge to construct a reasonable answer by filling in any missing part. All right. Now, here, sometimes reconstructed reflections are incorrect. Remember our earlier discussion on long-term memory, there are gaps, right? We don't recall everything, but there are gaps or there are holes that we are likely to fill those holes without even being aware of it, okay? With our biases, our stereotypes, that type of thing. So, and very, very early experiment, but meaningful. Bartlett conducted a series of famous studies on remembering stories. So essentially, he read a complex, unfamiliar Native American tale to his students at England's Cambridge University. And after various lengths of time, he asked the students to recall the story. So he actually found this. Students record stories were generally shorter than the original. Okay, that's the first finding. The second one is that the recalled stories were translated. That is to say, Seal Hunt trip was remembered as a fishing trip. So instead of remembering the exact words of the story, the students remembered the meaning. But the meaning they remembered was altered slightly to fit their cultural expectations and stereotypes. Okay? In other words, they are schemas, right? They are schema. So you see here, our long-term memory is not perfect, far from perfect. Is that right? Here, cultural influences, stereotype may affect how we recall from long-term memory. Right? So let's take a look at what this here, the summary. Right? Summary here. Yeah, sensory, memory, temporary capacity, very capacity is high, cost but then we have to we have to pay attention to all those available stimuli. Duration, a quarter second for vision, 4 seconds for hearing, right? And then short-term memory, also our working memory, the capacity is 7 plus or minus 2. The duration is about 20 to 30 seconds. Right? Long-term memory, wow, it's like our hard disk, a good hard disk. Okay, it's relatively permanent storage of information. Okay, now capacity likely to be a limited duration long. Okay, so here. Now, information, remember the broadbands, bottleneck, phenomenon, right? So, that is an attentional gate, okay? Has to be information has to pass through this. So therefore, even though this is capacity is high, when information comes here, only a very small set of information will get past the attentional gate, right? Elaborative rehearsal, that's the information subjected to elaborative rehearsal or deep processing, say processing the semantic aspect of the information, or process the imagery. Okay, if you read Alan Pavion. All right. So now information in long-term memory appears to be lost through time decay and interference. Okay, but then information lost from short-term memory truly disappears. Right? No amount of effort will bring it back. But information stored in long-term memory may be available given the right cues. Right? So information appears to be lost from long-term memory through see here, through time decay and interference. Right? Now, a very longitudinal study by Anderson, back in 1990, he found the following. Memory for Spanish English vocabulary decreases for about 3 years after a person's last course in Spanish, English-speaking subjects, okay? Then stays level for about 25 years, then drops again for the next 25 years. Okay, one explanation offered by Anderson is the following: that for this decline, the one explanation for this decline is that the neural connections, like muscles, grow weak without youth. That is very true for a human, right? After 25 years, it may be that the memories are still somewhere in the brain, but are too weak to be reactivated or to be retrieved. Okay? Now, what is what? Then interference, the idea that interference causes forgetting in long-term memory as well as in short-term memory seems to be supported by evidence from research. Okay? Now, and say electric shock therapy, subjects going through what electric shock therapy, then what? Then all of a sudden, what? After electric shock, they what? They remembered a lot of things. They thought they forgot. Okay, so forgetting in long-term memory is almost non-existent. Now, have you heard of the time tunnel in life after death report? If you read, I think if I remember correct, I read all of them on 30 some years ago. I think it's Raymond Moody, okay, if I remember correctly. Now, Raymond Moody, he wrote many books, okay, about what life after death. That is to say, there are quite a good number of people who were declared dead by the hospital, but later on they quote unquote they woke up. Now, so Raymond Moody, he conducted scientific research. He actually interviewed those people, so he tallied all those people. Okay, so he came up with the general finding. Okay? What finding? Well, most subjects reported after they were declared dead, they felt that they used the word soul, felt the soul leave the body, and the soul was floating in the ceiling, close to the ceiling, and what the soul could see doctors, nurses trying to resuscitate the patient, as to say the person, without success. Then all of them, almost 95% of them, they reported being transferred to a time tunnel. Okay, time tunnel with light at the far end of the tunnel. And then they were moving at the speed of light through the tunnel. And then every single act they did while they were alive came back to them. Came back. All the good stuff, the bad stuff, embarrassing stuff, everything. They remembered everything. Okay. And at the end of the tunnel is a light figure. And of course, here, a lot of them reported seeing Jesus. Okay, that type of thing. Okay, so that means everything is laid down in our memory. Okay, so that's a statistical report, okay, of all those people who were declared dead. They came back and they reported this. Okay, so there is some truth in that. Okay, some truth in that. But then, of course, here you understand that in our society, if there is a phenomenon science cannot explain, most scientists will stop trying to stop looking into it. They think, no, this is abnormal, or this may be an illusion, that type of thing. Okay, but then if you if you're bilingual and you are bicultural, that type of thing, you will see that well, a lot of stuff was reported in one culture, okay, reported in one culture, can also be found in our culture, but we tend to disregard those. Okay, anything that cannot be explained by logic will be belittled. Okay, so that is the truth. Okay, I can tell you this. Okay, there are a lot of stuff science fails to explain, but they are so true to a lot of people. All right. Okay, so let's move on now. Physical location of memory trace. Uh, well, let us take a look at our genes. The genes are compared of DNA and RNA located in the chromosomes, okay, which lie in the nucleus of every cell in the body. And there are 23 pairs of genes. Okay, 23 pairs of genes, okay, in the chromosome. So DNA contains chains of atoms, the helix shape, okay, by Watson, okay, and Francis Crick. So DNA contains chains of atoms and molecules that code and store information about our growth and development. Right? Of course, animals also have genes, all right? So it can reproduce itself exactly. That is to say, it achieves self-duplication. Okay, the coded information in the DNA molecule is transmitted to the other parts of the cell by the RNA molecules. Okay, remember here we have mRNA vaccines. Okay, so let me continue. Okay, so DNA acts as the blueprint, okay, for the formation of certain enzymes that help to guide the development of the organism. So DNA can be thought of as the architect's blueprint, okay, while the RNA would be the builder, translating this blueprint into a house. For example, our DNA makes sure that we humans won't grow into a pig and vice versa. Okay, so RNA in a way enforces this, right? So RNA actually tells our cells what to make, which type of protein to make, that type of thing. All right, so let's take a look. Then now you understand something about our DNA and RNA. So let's take a look at this classic experiment. Haydn suggested that we are born with roughly 10 billion brain cells. Okay, and that within each of these cells there are millions of RNA molecules. You see the number staggering. That right? So what the number, just the sheer number staggering. Well, then the RNA theory could logically account for trillions of images and memories that we have. Right? So Haydn did an experiment and found that changes in RNA within nerve cells occurred as the direct result of environmental stimulation. Okay, and I will talk more about some of those studies. So this here suggested that at least RNA plays a role. All right, so let's take a look at this one. McConnell and Jacobson. Early on, what this has been repeated even more at Nicholson's neuroscience labs. Okay, these two researchers back in many years ago. They experimented with flatworms, planaria. Okay, they trained flatworms to respond to a condition or stimulus, say a light source. Okay, then after that, so the flatworms learned that. Then what? Then the experimenters cut them into halves. Say one flatworm, now cut it into two halves. Then the heads regenerated the tails, and the tails regenerated the heads. All of the new flatworms, planaria, retained the conditioned response. Okay, they respond to a conditioned stimulus. So that's called a conditioned response. Okay, so all of these new planaria, the head from the tail regenerate the head, all of them retained the conditioned response, retained the learning. So this experiment indicates that perhaps memory could be chemical in nature. All right, chemical in nature. All right, since under certain conditions, flatworms will eat one another. That's true. Okay? So now we have one researcher that after grinding up trained worms, and feeding them to untrained worms, the untrained worms responded to the conditioned stimulus. Okay, so that means the conditioned response that the memory had been chemically transferred from one organism to another. Okay, isn't that fantastic? Okay, look at another study, Horning and John. They cut trained worms into halves and allowing the half to regenerate in normal pond water versus a solution of ribonucleus. Now, see here, solution of ribonucleus is is an enzyme known to break up RNA. It breaks up RNA. Okay, take a look at the results here. Okay, they cut the flatworms into two. Here in normal pond water, okay, just that one. This here, they had generated the tail and then the what is it? The head generated tail, okay, and then the conditioned response was kept. Here, the tail generated the head, and the conditioned response was kept. That means learning in pond water, head generated tail, the learning was kept. Tail generated the head, learning, the conditioned response was kept. Look at this here. Solution of ribonucleus. It breaks up the solution broke up RNA. Okay, well, head generated tail, the response was kept. Tail generated head, no, there's no the condition response was not kept. All right, so what does that mean? Well, in the flatworms, heads contains 75% of the nervous system. The coded RNAs are retained in the head, says here. Okay, and what the solution prevented the coded RNA from being duplicated in the new head cell at the head cells here. Okay, but not here because it was 75% of the nervous system in the head. Right, so the conclusion here, it seems that RNAs are involved in the memory process. And finally, what the conclusion was, short-term memory largely electrical, and that's why what is so fast, decay is so rapid, or electrochemical in nature. Okay, and therefore what decay is what fast. Long-term memory largely chemical in nature and perhaps RNA dependent. Okay, so what long-term memory chemical in nature, and therefore what it retains what this what memory, okay, quite steadily. All right, so let us take a look at what applications of information processing for teacher. Okay, for teacher. Now, this one here, let's take a look at how do we apply what we have learned from memory research studies to what in the classroom or for the teachers. First, make sure, okay, that the teacher has what teachers have the students' attention. All right. So how do we do that? You want in the classroom, the teacher develops a sign or a signal that tells students to stop what they are doing and focus on what? On you. So you as a teacher. Okay. Now, something like this here, like this claps hand. Okay. Whenever the teacher does this, okay, then every student should drop whatever they are doing and pay attention to the teacher. And well, honestly, students would like this. So sometimes what teachers would ask them, you do that, okay? When I clap this, you clap the same thing, and you want say having to clap that means that the students have to drop whatever they're doing and pay attention to the teacher. Is that right? That's very effective, especially for young students. Okay, they like this. Okay, then some teachers move to a particular spot in the room, flick the lights on and off, or play a chord on the class piano. So these are signals for the students to stop whatever they're doing and pay attention to the teacher. Okay. Other ways to draw the students' attention would be like move around the room, use gestures, avoid speaking in a monotone, right? Or you begin a lesson by asking a question that stimulates interest in the topic. Okay, that type of thing. Okay, or regain the attention of individual students by walking closer to them, using their names or asking them a questions just to let them know you are paying attention to them, and likewise you want them to pay attention to you. I look at the second point here, help students separate essential from non-essential details and focus on the most important information. How to do this? Well, summarize instructional objectives to indicate what students should be learning. They relate the material you are presenting to the objectives as you teach. Right? And also, when you make an important point, pause, repeat, ask a student to paraphrase, note the information on the board in, say, colored chalk. You see, Peter has so many different colored pen. Or you tell students what to highlight the point in the notes or readings, right? That type of thing, right? So help students. Number 3, help students make connections between new information and what they already know. So that means what? Something like elaboration, is that right? Now, so review what prerequisites to help students bring to mind the information they will need to understand new materials. Okay. Another example is that use an outline or a diagram to show how new information fits with the framework you have been developing. Okay? So that will help, right? Number 4, provide for repetition and review of information. Teacher can do this here. Begin the class with a quick review of the homework assignment. Okay, so repetition, review of information. Well, give frequent short quizzes. Okay, so that's a good idea. Okay, frequent short quizzes. Okay, or you build practice and repetition in the games, or have students work with partners to quiz one another. And so, you know that a lot of teachers do this. Okay, present material in a clear, organized way. To say, to make the purpose of the lesson very clear, and perhaps give the student a brief outline to follow. Then at the end of the lesson, use summaries, okay, or sometimes even use summaries in the middle of the lesson. Okay, it's just to clarify, to give more clarification. Number 6, focus on meaning, not memorization. Remember the level of processing experiments. Okay, so semantic processing trumps phonemic and structural processing. Okay, say sheer memorization. Sometimes students are just processing the structural aspect or the phonemic aspects of the materials. It's not good enough. All right. So say for example, in teaching new words, help students associate the new word to a related word they already understand. Right? Now, so that kind of thing. So say for example, in teaching division, you have remainders. Okay, for example, you want to divide 15 by 4. So how do you do that? So you give them 15 coins or whatever, and then let them count 4 in the group, 4 in another group, 4 in another group. Then they will come up with the remainder. That's how you could teach them division, and of course remainder. Okay, all right. Metacognition. What is it? Well, that is the executive control processes. Okay? That is what the metacognition means. What people's awareness of their own cognitive machinery. Okay, let's take a look here. Metacognitive skills. Say this is what actually the executive control processes. Okay, which include what? Include the following. Okay, selective attention, rehearsal, maintenance rehearsal, elaborative rehearsal, organization, and what? Elaboration. Okay. Now, these executive control processes guide the flow of what? Information through the information processing system. Okay, through the information processing system. So, metacognition literally means knowledge about cognition. Does it say what? Does it say what? People's awareness of their own cognitive machinery and how the machinery works, because what people differ in their metacognitive knowledge and metacognitive skills. They differ in how well and how quickly they learn. Okay? Now, some of the differences in metacognitive abilities are due to development. Okay, as due to development. As children grow older, they are more able to exercise what executive controls and use strategies. So metacognitive abilities begin to develop around what age 5 to 7, and then what improve throughout school. And most children go through a transitional period when they can apply a particular strategy if reminded, like repetition, like rehearsal, but will not apply it on their own. Okay? Young children do not know that rehearsal can keep the memory in the working memory longer, and what likely they can remember it. Okay, they don't know how to do that. Okay, but then mature students they will do that without having people tell them to. Okay, so that maturation will bring about this realization. Okay, the spontaneous realization. Right? Now, of course, not all differences in metacognitive abilities have to do with age or maturation. There is great variability, even among students of the same developmental level. Some individual differences in metacognitive abilities are probably caused by by biological differences or by variations in learning experiences. Okay, so there are factors. So then let me give you an example. Actually, results of many studies. Students who excelled in mathematics remembered numbers and locations significantly better than students talented in verbal areas. The verbally talented students, on the other hand, had better memories for words. So based on these results, researchers believe that basic differences in information processing abilities play a role in the development of mathematical and verbal talents. Okay, now because working memory is limited. Our working memories, short-term memories, very limited. 7 plus or minus 2. Remember these numbers. Okay, students, particularly younger and less able students, they often try to simplify new information by ignoring some elements. And these what leads to errors. Right? So they try to ignore some information, perhaps due to the limited capacity. Right? The limited capacity. All right. The importance of knowledge in learning. Okay. Now, the here knowledge is the outcome of learning. Okay, the outcome of learning, and knowledge is more than the end product of previous learning. It also guides new learning. Okay, now in terms of learning, it has to be related to memories. Okay, that I just mentioned that young children have very limited working memories, but their memory span improved with age. It is not clear whether these differences are due to changes in memory capacity or improvement in strategy use. Right? Now, it has been suggested that the total amount of space available for processing information is the same at each age, but young children must use quite a bit of this space to remember how to execute basic operations. Okay, using new operation takes up quite a bit of the child's working memory. That is true. Once an operation is mastered, however, there is more working memory available for short-term storage of new information. So then what? Take a look here. Then biology? Then biology may play a role too. As the brain and neurological system of the child mature, processing may become more efficient so that more working memory space is available. So then what? The more knowledge can be stored. Okay? As children grow older, they develop more effective strategies for remembering information. Remember, I just mentioned most children spontaneously discover rehearsal around age 5 or 6. This one is an experimental finding. Younger children, younger than 5 or 6, can be taught to rehearse and will use the strategy effectively as long as they are reminded. But they will not apply the strategy spontaneously. Children are 10 to 11 years old before they have other working memories. Now remember, 10 to 11 years old, that is very close to Piaget's formal operational stage. Okay? So therefore they are more capable, is that right? All right. Now, I mentioned that young children often use reasonable but incorrect strategies for solving problems simply because of their limited memories. So they try to simplify the task by ignoring important information or skipping steps to reach the solution. Okay, this puts less strain on memory. Okay, now remember Piaget's experiment on the concept of conservation. Young children may consider only the height of the water in a glass, but not the diameter of the glass, because this approach demands less of their memory. Right? So this explains that young children's inability to solve the classic appreciation conservation problem. Around age 6, most children discover the value of using organizational strategies, and by 9 or 10, they use these strategies spontaneously without having people to remind them. Right? So let's come back here. The importance of knowledge in learning here. Knowledge is the outcome of learning, and learning has to do with transferring information from short-term memory to long-term memory, right? So once we have knowledge, and it is not the end product of previous learning, it also guides new learning, because because whatever stored in the long-term memory can be retrieved to guide future learning. Right? Now, the cognitive approach suggests that one of the most important elements in the learning process is what the individual brings to the learning situation. Okay? What the individual brings to the learning situation. So what we already know determines to a great extent what we will learn, what we will remember, and what we will forget. Okay? Let me here. Excuse me. My allergy. Two researchers shows the importance of knowledge in understanding and remembering new information using junior high students. They all read a passage describing a baseball game and were tested in a number of ways to see if they understood and remembered what they had read. Right? Now, here, let's take a look. Take a look at the result of the experiment. So here we have baseball knowledge. Okay, this is poor, good baseball knowledge. Okay, then we have reading skills here. Okay. Yeah, reading skill. Because this is good, this is bad, reading skills. All right. Now, take a look at the result. Okay, take a look at the result. Okay, if they understood and remembered what they read. Now, here, baseball knowledge pool. Okay, and they remember far better than this here. They remember the list. This one here, remember the list. All right? And of course, for good reading skill, but then with good baseball knowledge, of course, they understand more than this here. All right? More than this here. And for good baseball knowledge, okay, whether they have good reading skill, bad reading skill, no difference. Equal, no difference. All right? And of course here, with good baseball knowledge, even if they have bad reading skill, this one here, this one performs much better than this. Okay? And now take a look here. Okay, that is to say, this one is what? Good baseball knowledge, but bad reading skill. They understood more than those subjects with poor baseball knowledge but good reading skill. Okay. Well, once you have good baseball knowledge, perhaps they have already played the game and all that. They understood far more than this. So these are significantly more than equal. All right. So this is the what? This is what knowledge interacting with reading skill. All right. Okay. Now, or is it? Oh, here. Kinds of knowledge. Okay. Now we have what general knowledge. We have a general knowledge, domain-specific knowledge. We have declarative knowledge, procedural knowledge, and conditional knowledge. All right, so take a look at what examples. So general knowledge is applied to many different situations. For example, general knowledge about how to read, how to spell, how to use a computer. It is general knowledge. Domain-specific knowledge pertains to a particular task or a particular subject, right? Let's take a look at declarative knowledge. That is knowing that something is the case. The common use of the term knowledge usually refers to declarative knowledge. Okay, facts, beliefs, theories, opinions, poems, passages, lyrics, rules, names, and so on. The range of declarative knowledge is tremendous. Okay, so most of the time we call knowledge is declarative knowledge. Procedural knowledge is knowing how to do something. Okay? To show procedural knowledge, one must act. Say how to drive a standard shift vehicle. Right? Conditional knowledge is knowing when and why to apply your declarative and procedural knowledge. Okay, for example, it takes conditional knowledge to know when to apply one procedure, okay, when to apply another procedure. Okay, so it takes conditional knowledge to show when to read every word in a text and when to skip those words for learned speed reader. Speed readers tend to skip words, right? Unimportant words, right? So that's why when they could skip, they read fast, right? All right, so take a look at development of declarative knowledge. Okay, now declarative knowledge is learning that something is the case, all right? And you know what we just mentioned, that the range of declarative knowledge is tremendous. Okay, but within the information processing perspective, to learn declarative knowledge is really to integrate new ideas with existing knowledge and then construct an understanding. Right? There are several ways to do that. Rote memorization. Okay, there are times when we have to memorize something word for word. For example, to recite a poem. Okay, or remember the lines in the song, the lyrics. Okay, a play. Okay, we tend to remember items at the beginning and at the end of the list, but then we tend to forget those in the middle. This is called the serial position effect. Okay. Now, part learning, what is part learning? Part learning is breaking the list into smaller segments can help prevent the serial position effect. Now, let me show you what is the serial position effect. Okay. Now, let's say what here. Good. Okay. This is what memory. Memory measured by number of words one can recall. This is serial position. For example, outside of the screen, serial position is good. Say this is the first word presented. This is the second, the third, and this is the last one, last word presented. Okay, that one. After the last word has been presented, you are asked to recall everything, all the words. Okay, so psychologists have found the following. This is called the serial position curve. Is that here, memory is good for the first and one level up, and then towards the end, like this. Okay, so our memories for the last few words, very good. See here, very good. And our memory is for what? This is called the what? The primary effect. This is called the recency effect. All right. So we remember these words far better than those in the middle. And we also remember these words here far better, not far, but better than those words in the middle. This is called the serial position effect. All right, so it's this here. Okay, now part learning can help us avoid this stuff. How do we do that? That is to say, we do not learn such a long list. We chop it up. Say we learn just a few words here. Then we learn this, and we learn this, and then we learn this, and then we learn this. Say we chop up the long list into shorter list to learn. So within a shorter list here, there is no serial position effect. Is that right? Right? Let's say what? Let's say here. Say here. Okay? So it will not be like this. Okay, it will be what? Because the list is shorter, the likelihood is good that what? It will what? It will be what? Say it will be flat like this. So that's part learning, right? Part learning. All right. So that's part learning. So breaking the list into smaller segments can help prevent this serial position effect. But because you breaking a list into several shorter lists means there will be fewer middle items to forget. All right. Another strategy for memorizing a long selection or a long list is the use of distributed practice. Okay, well, distributed practice is more effective than master practice because long study sessions lead to fatigue and motivation lacks. Okay, what does that mean? Okay, let me show you here. That is bad. All right. What is it? I'm talking about distributed practice. Well, let's say you must have done this, is that what tomorrow is the test, and you cram everything the night before, is that right? That the night before the test you study until until the wee hours, okay? And you hope that you could remember everything during the test, but that's not good, because this is called master practice, right? You study long and hard without stop, okay? Now, distributed practice means the following, and it is much better than master practice, okay? Okay, let's say here, this is master practice or master study. This is time you spend studying, time. Okay, this is 0, this is 6 hours. Non-stop, you go from here to here non-stop for 6 hours, okay, versus distributed. You do what? You study hard here, and then you break, then you come back, study, break, come back, study, break, come back, and study. Well, let's say the total time you spend here, 6 hours straight here, you have maybe I don't know, 1.5 hours, 1.5, okay? Anyway, altogether 6 hours. Then you remember far more here than here with breaks. Now, those breaks can be saved. Let's say it is let's say a chemistry test. Okay, you study, of course, you study chemistry. Okay, so here the break, you just you could do whatever you want, but not chemistry. Okay, you could study let's say here, okay, English here, you study English, but not chemistry. Okay, you spaced studying for chemistry. You don't go from here to here, but then you space it. Okay, just spend so much time here, then you switch your attention to something else. Come back to it, then leave it, something else, and so on. This is called distributed practice versus mass. This is far better than that. All right. Okay. All right. Now the likelihood the long study here contributes to fatigue and motivation lack. Okay, so that's what psychologists believe. Mnemonics, of course, here we already discussed this. Okay, making it meaningful. Well, on the basis of what we've learned from level of processing. All right, so the best single method for helping students learn is to make lesson as meaningful as possible. Okay, new terms are clarified through associations with more familiar words and ideas. Meaningful lessons are also well organized with clear connection between the different elements of the lesson. Okay. Now, finally, meaningful lessons make natural use of old information. Okay, of use of old information to help students understand new information through examples or analogies. Okay, or analogy. Okay, all right. So let's move on. Procedural knowledge. How do we do that? Well, much of experts' decorative knowledge, that is to say, facts and verbal information, has become Well, the term proceduralized. That is to say, incorporated into what routines that can be applied automatically without making many what demands on working memory. Skills that are applied without what conscious thought are called what automated basic skills that are applied without what conscious what thought. Now, for example, shifting gears in a standard transmission car. All right. Okay. So, like what at first you have to learn how to coordinate, release the clutch, step on the gas, and that type of thing. And very soon, once you have learned that, it becomes one automatic. Okay, so the skills that are applied without conscious thought. Okay, so however, the thing is that no matter how expert you are in driving the standard shift car, you still have to consciously watch the traffics around you. This kind of conscious procedure is called a domain specific strategy. All right. So, but then let's come back and take a look at what automate the basic skills. As most psychologists identified what three stages in the development of an automated skills. So the first one is what cognitive stage. When we are first learning, we rely on what that creative knowledge and general problem solving strategies to accomplish our goal. Now, for example, I like to use this example to learn how to engage in first gear while synchronizing the footwork. So we need to understand the working mechanism of the clutch and the engine. I think that's the cognitive stage. Then the associative stage, individual what steps of a procedure are combined or chunked. Remember chunking in working memory, chunked into larger units. For example, changing gear and footwork become synchronized smoothly. Okay, you associate two of them, and before long you could do that. Okay, you just synchronize. An autonomous stage where the whole procedure can be accomplished without much attention. So therefore, once you achieve this state, you could drive. Okay, you could drive, and then at the same time you could talk to your passenger. Is that right? You could do lots of things. Okay, I'm not encouraging you to do that, but I'm just giving you an example that once you get past that stage, okay? All right. So to help students pass through these three stages, two factors are critical. Okay? That is to say, what prerequisite knowledge and what practice with what feedback. Okay, and these two are critical to help learners pass through these three stages. Right? Now, if students don't have the essential prior knowledge, like schemas, skills, etc., the load on the working memory will be too great. So in order to compose a poem in a foreign language, example, you must know some of the vocabulary and grammar of that language, and you must have some understanding of poetry, forms, to learn the vocabulary, grammar, and forms as you also try to compose the poem would be what? Too much. Okay? Would be too much. All right. So, practice with feedback. What is it? Practice with feedback. Here you have one automated skill. So practice with feedback here. Okay, allows you to form associations, recognize cues automatically, and combine small steps into larger condition action, okay? Larger condition action rules or production, okay? So even from the earliest stage, this practice should include a simplified version of the whole process in a real context, not isolate the practice on sub-skills disconnected from the situations where the skills might be applied. So practice in real context helps students learn not only how to do a skill, but also why and when. All right. So an example is what driving a car in a computer simulation versus driving a car on the road. Right? So development of conditional knowledge. Okay, development of conditional knowledge is that conditional knowledge is one knowing when and why to apply your declarative knowledge and procedural knowledge. Well, for example, it takes conditional knowledge to show a speed reader when to read every word in the text and when to skim them. Right? So experience and practice can aid the development of conditional knowledge. All right? So that's what knowledge, a lot of knowledge, is that right? Okay, so knowledge is kind of intimately associated with what? The use of what? Memories, right? Okay, good. Thank you.